Hello and welcome back, my fellow mathletes. We're looking at B4 in this video, B4 from our open paper from 2016. Let n be a positive integer. Given a real number x, this is called the floor function, so let floor of x be the greatest integer less than or equal to x. For example, the floor of 2.4 is 2, the floor of 3 is 3, because 3 is already an integer. Floor of pi is 3. The floor of something like negative 7.1 is negative 8. You might think it's negative 7 because you might think, oh, we're just chopping off the decimal part, but this is not the case. Negative 7 is greater than negative 7.1, so we actually want negative 8 because it's an integer that is less than or equal to negative 7.1. Okay? So there's the floor function, fairly common function, it along with the ceiling function that's written a little differently. These guys are useful. They pop up on contests from time to time. What have we got? So define a sequence A1, A2, A3, where A1 is equal to n, this positive integer that they started off with. And we're going to let AM, so the next term in the sequence is defined by taking the current term, dividing by 3, and then floor function. So we're always going to get a sequence full of integers, because the floor function takes in a real number, spits out an integer. Alright, the sequence stops when it reaches 0, which it inevitably will, because we keep dividing and dividing and dividing and rounding down. The number n is said to be lucky if 0 is the only number in the sequence that is divisible by 3. For example, 7 is lucky, since 7 divided by 3, you'll get 2 and a third. Floor that to 2. 2 divided by 3 would be 2/3. Floor that to 0. And so 7 and 2 are not divisible by 3. That's all it takes for 7 to be lucky. Incidentally, this also shows that 2 will be lucky. So I think we can sort of build up lucky numbers. You're lucky, so you might say n is lucky if n over 3 is lucky and n is not a multiple of 3. Because if you're a multiple of 3, you've got no help because you're going to be the first term in the sequence. And now they show 10 is not lucky since 10 goes to 3, goes to 1, goes to 0, but as soon as you see that 3, you're unlucky because it's a multiple of 3 in the sequence that isn't 0. Alright, determine the number of lucky positive integers less than or equal to 1,000. Okay. Well, I might start by taking a look and saying, alright, let's look at some of these numbers. So we'll start forming the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll go all the way up to 10, sure, why not? So we know 10 goes to 3, goes to 1, goes to 0. 9 divided by 3 is just going to be 3, which goes to 1, goes to 0. Actually, 1 goes to 0, 2 goes to 0, 3 goes to 1, goes to 0. And you'll notice that we really are just building off the previous work. 4 goes to 1 1/3 when you divide it by 3, so that goes to 1, goes to 0. 5 goes to 1, goes to 0. 6 goes to 2, goes to 0. 7 goes to 2, goes to 0. 8 goes to 2, goes to 0. So we can definitely sort of see some of the same work going on. When we hit 12, we hit 4, and then we should just copy what 4 does. 13 goes to 4, goes to 1, go to 0. 14 goes to 4, goes to 1, go to 0. 15 goes to 5, which goes to 1, goes to 0. 18 would go to 6, which goes to 2, which goes to 0. Alright, so we've got a few of these. We're definitely noticing something as we write the sequences out, heading downwards. And, alright, how do we get lucky numbers? How do we get unlucky numbers? Because, of course, there's two ways to count the number of lucky numbers, less than or equal to 1,000. We could count the lucky numbers directly, or if we find that it's easier to count the number of unlucky numbers, we might instead choose to do that and subtract that number away from 1,000. Okay? And it might be easier to get the unlucky numbers because they start with a 3. So this 3 here appears in 3 other later numbers sequences and therefore makes them unlucky. So this 3 early on gives us 3 more later on that are unlucky. This 6 already unlucky, but it gives us more later on that are unlucky. And so it sort of builds up like that. So we might take that idea and run with it. We could also investigate what we're looking at a bit more. So for example, well, how does this process work? Okay. Well, if I start with something that's, dividing by 3 seems to be quite important. So maybe if I let n be 3k plus r, and r is the remainder, so it's 0, 1, or 2, n over 3 is just going to be k plus r over 3, and n over 3 is just going to be k. So if we're looking at a lucky number, say 4, we'll use green. So we're looking at 4. 4 will later on appear as sort of the next step after 3 numbers. 2 of them will be lucky numbers as well. One of them will have to be a multiple of 3. So, okay, so if n lucky if n is equal to 3k plus 1 or 3k plus 2, and k is lucky. So this is a nice, useful fact. I think we can use... So what I'd like to do is maybe run a little test. We've got the numbers 1 to 20 out here. I haven't counted how many are lucky or unlucky. Let's see if we can theory a way to count it as is. So, for example, I might start by saying something like, define 0 as lucky. Okay? I know 0 doesn't count, but define 0 as lucky, and then what can come before 0? Well, you could have, doesn't work out quite as nicely as I would want. So maybe don't do that. Maybe not write that down. Of course, remember, it's a B-part question, so we do just need our final answer. But I like writing down things, especially for B4, just because it's often a much harder question, and I do want part marks if I screw up a calculation or something like this. So, for example, 1 is lucky. What n have... So what A1 have A2 equal to 1? Well, 3, 4, and 5. So 1 gives 2 more lucky numbers. And so my thought is we start with 1 and 2, and they work backwards to 3 numbers, but one of those is always a multiple of 3. So we start with 1 and 2, but then gives us more lucky numbers working backwards. 7 and 8. And then 4 gives us 2 numbers, which would be 13, 14. And 5 gives us 2. Everything except 15. Of course, 15 does lead into... Maybe I should put the arrows the right way. So 16 and 17, not multiples of 3, but they do have 5 as their next term. So it sort of grows out like this, and there won't be any number that's in both lists. Because think about the smallest number that happens to be in both lists. Okay, its next term has to be something over here that leads to a 1, but its next term also has to be something that leads to a 2. Well, then clearly it's not the smallest number that's in both lists. And so what can lead to 7? 22 and 23, 25 and 26. We also might notice that, oh, there seems to be sort of tiers of numbers. Now, there's 2 numbers from 0 up to 3 that work. There's 6 numbers in total. So there's 4 more here. There's 8 more here. So that's kind of interesting. There's certainly powers of 2 patterns going on here. What else could we do? Well, we could say, suppose. So let's do it this way. How many numbers? I was going to say how many numbers in a certain stretch, but that's not going to work out. So, from 0 to 3, there are 2 lucky numbers. From 4 to 9, I suppose I could include 1 here. There are 4 lucky numbers. From 10 to 27, there are 8. So just keep going with the powers of 2. From 28 to 81, and then 243, and 729, which for some reason I started writing backwards. Okay. And the reason this works is because until we reach a certain amount, each one of these is always going to give us 2 more numbers. And in fact, you can keep going from 730 to the next power of 3, which is 2187. So we can keep going. There are 16. There should be 32. There should be 64. Should be 128. Now, I'm not that enthusiastic about this range of values here, just because 1000 is somewhere in here, and it's going to be kind of hard to cut it off. Okay, so I think well, I like this, that we have a nice count. Now the question is, how many lucky numbers are there between 730 and 1000? Okay, because we can do 2, 4, 8, 16, 32, and 64. That's not a thing. That's not a problem to add up. It's just going to be 126. Because it's going to be powers of the next power of 2 minus 2. So 126. We'll keep that. But now my question becomes, how many lucky numbers from 730 to 1000? Okay. Well, again, the same sort of reasoning applies. Any lucky numbers in the range from 244 to 729 will start to spit out 2 of them. There's just a question of, well, what's the cutoff? Well, it should be 2 times the number of lucky numbers from 244 to 500, right? Do we just sort of... Yeah, because any lucky numbers in this range should be twice the lucky numbers. Yeah, each lucky number in that range will double, will give us out 2 more lucky numbers. And if it's up to 500, then it's guaranteed to be in this range here. No, not 500. Not 500. It's got to be 1,000 over 3. So how about up to 999? And then I'll later ask, what about 1,000? So from 244 to 333, how many lucky numbers are there? And that should be 2 times the number of lucky numbers from 82 to 111. And that's also a multiple of 3, so equals 2 times number of lucky numbers from, what was it, 82, so it would be 28 to 37, and this is not a bad thing to try and work out, so let's just get it. 28, 29, 30, 31, 32, 33, 34, 35, 36, and 37. I didn't space that out properly. Let's do it nice and neat. Now I just want the lucky numbers, so we can automatically ignore multiples of 3. These two would go to 12, which is a multiple of 3, so let's ignore that. These ones would go to 11, that's fine. But 11 goes to 3. So they're out. These would go to 10. 10 goes to 3. So they're out. And these ones here go to 9, so they're out. So are there really no lucky numbers from 28 to 37? It's possible, I guess. So then that would mean that there's no lucky numbers between 730 and 999. So I pick one at random. If my work is correct, if my thought process that every lucky number produces 2 more lucky numbers in a larger range, then in theory, if I pick a number like 861, which adds up to 15, so let's pick something else that isn't a multiple of 3. 862. This should not be lucky, so let's divide it by 3. And 3 goes into 8 2 times. 3 goes into 26 8 times. So 24, bring down the 2, and 3 goes into 22 7 times, so this would go to 287. Not a multiple of 3. So let's divide it by 3. 3 goes into 28 9 times. 3 goes into 17 5 times. 95 is not a multiple of 3. So it's starting to blow a hole in this idea. 3 goes into 9 3 times. 3 goes into 5 once. You see how it does work down to a number in a specific range, but 3 goes into 3 once, and we're going to get 10. 3 goes into 10 3 times, and it won't work out. So, there are no other numbers in the range 370 to 999 that matter. Great. So, it looks like we were worried for nothing. The answer should be 126 or 127. Let's not forget the number 1,000. Because they do say less than or equal to 1,000. So is 1,000 in the range? Now if we wanted to, we could double check and our guess and say, pick another random number in this range, like 911. Okay, does that work? We get 103 here. 103 would go to 34. And 34 would go to 11. And 11 goes to 3, which would not be lucky. So the only question now is 1,000. This little extra case. How many times does 3 go into 1,000? 333, multiple of 3, so it's not going to work out. So the final answer is 126. And there we have it. All right. So 126 is our final answer. Not a bad question. I'm sure there were other ways to do the question, rather than just this sort of working backwards and taking lucky numbers to produce more lucky numbers. But I certainly liked it. I like the simplicity of the tree and things like that. Yeah, so that finishes off Part B of our contest. I will see you for Part C of the 2016 Open in the next video. Until then, take care and have a wonderful day.